So, but by now, let us just continue with the stuff from yesterday. Yesterday we stopped with this figure here, yeah? I introduced you into the nesosilicates, the sorosilicates and the cyclosilicates. And now we will continue with the chain silicates, the double chain silicates and the sheet silicates. So for those who enjoyed yesterday not the class, then just check it with the movie which we uploaded. You uploaded yesterday the URL of the movie? Or? Not yet, but he will do it today, yes? Then you can do on Saturday or on Sunday, you can watch me and then just download these things here, these minerals and rock PDF, and then you can just go through. So in the stuff which I have written on the board, and for those who did not come yesterday, you should just get it from somebody else, yeah? That's the way how it is. So, and we stopped yesterday with this figure, and now let us just continue with the next figure. So these are the chain silicates and the double chain silicates. And these chain silicates and double chain silicates are called the inosilicates. So, and chain silicates, these are the pyroxenes, yeah? So we have here the chain silicates. So in chain silicates, as I just told you, these are the pyroxenes and the pyroxene leads. So, and these are single chains, and that you can see here, and here there are the tetrahedrons are connected just to a chain. So, and now I will give you the mineral chemistry for the most important end members from the pyroxenes. So, in the pyroxenes can be subdivided in autopyroxenes and clinopyroxenes. So, the autopyroxenes are called autopyroxenes because they are orthorhombic. Yeah, orthorhombic is also a crystallographic system. So, in the clinopyroxenes, they are monoclinic. So, let us just start with the autopyroxenes. Here we have the autopyroxenes, then we make here a second group. These are the clinopyroxenes. Yes, so and from the autopyroxenes, we have two end members. One end member that is the N-statite, and the other end member that is the ferrosilite. So in the N-statite or the pyroxenes, they have also two M spaces, and one is the smaller one and two is the bigger one. Then we have the tetrahedrons, and here we have the oxygens, and all pyroxenes on this planet has 6 oxygen, yeah? The garnets has always 12 oxygens, the feldspars have 8 oxygens, the olivines have 4 oxygens, and these pyroxenes have always 6 oxygens. So, and then you know by now we are talking about silicates, and if you are talking about silicates, then we have here on the tetrahedron side the Si, yeah? So, and now these autopyroxenes are orthorhombic, yeah? And if something or in this world is orthorhombic, that means we have it looks like this. How does it look like? So it looks like this. It is now not a perfect picture, but let us make it much better. So it looks like this, yeah? So, and then we have here an angle, and we have here an angle, and here we have here an angle. So, and these angles are called alpha, beta, and gamma, yeah? We are if we are talking about crystallographic systems, then we are talking always about room groups, and every room is a 3-dimension figure or a 3-dimension object, as this classroom here, yes? And this classroom here can also be described by 3 angles, yeah? And these three angles are alpha, beta, and gamma. So alpha, beta, and gamma is. So and if we have an orthorhombic mineral like this room is more or less also orthorhombic, then this angle alpha, beta, and gamma is 90 degrees. Yeah? So alpha has the same angle as beta, and beta has the same angle as gamma, and all these three angles are all 90 degrees. Yeah? So that is the orthorhombic system. So and if we are, and then we have here the lengths. We have here the length A, and here we have the length B, and that is C. So and if we are talking about the length of the axis, then we have A has the same length as B, but B and A is not the same like C. So and that is C, and you can see C is longer than A and B. Yeah? So and then we are writing A is B, but not the same like C. So and that means that A has the same length as B and C is longer. So why I'm telling this? I'm telling this if we have here always the same angles, then we need here on the octahedral side, we need atoms of the same size. Because if we are putting on the M2 space, we can put bigger atoms, yeah? There we can put bigger atoms, and then the crystal, the internal structure of your mineral becomes deformed, yes, and then the angles are no longer 90 degrees. Did you get it? Yes. So, and now we have to create the orthopyroxene, and then we are making just an Mg here and an Mg there. So then the formula of this orthopyroxene is Mg2Si06. Yeah? So and now we have created the orthopyroxene. So and now we are creating a ferrosilide, and which atom has nearly the same size as the magnesium? Iron, yes. And then we are doing again the Fm exchange, yeah? So we are replacing just magnesium with iron. Then we have here Fe and here we have Fe. So and there we have also, that's the same as for the olivines, we have this Fm exchange. And when I'm asking in the examination which pyroxene is formed or which orthopyroxene is formed at higher temperatures and which at lower temperatures, then you are answering me what? Always the magnesium end members are formed at higher temperatures. That is for the pyroxenes, that is for the olivines, that is for the amphiboles, that is for the garnets. Always the magnesium end members are formed at the higher temperatures, whereas the iron end members are formed at the lower temperatures. Yeah? Always. So and now we are going to the clinopyroxenes. Yeah? So and the clinopyroxenes are not orthorhombic, they are monocline. And if you are talking about a monocline mineral, then alpha is not beta, is not gamma. So there is one angle not 90 degrees, yes, and usually, and that is the gamma. So and that is because we are putting on the M2 space a bigger atom. So and then the whole internal structure of our crystal becomes then disaligned. Yeah? One cannot say deformed, let us say it is then not longer aligned. So if you are talking about clinopyroxene, I will give you now here the most 4 common end members. Yeah? I mean, in nature we have a lot of pyroxenes, yeah? Hundreds maybe, but I will give you just the 4 most important end members that we can play around with them a little bit in class. So the first end member here is the diopside. So and that means this stuff belongs to here, yeah? And this stuff here now in the that is orthorhombic. electron big. And this stuff here is monocline. So and that means alpha is beta, but is not gamma. So in alpha and beta, that is 90 degrees here. So and then we have A is B, but not C. So then we have the diopside, and we have the Hedenbergite. Then we have the Jadeit, and we have the Acmit. So if we are having now the diopside, we have again 6O, then we have here an Si, then we are starting always with the magnesium end member, then we have here an Mg, but now on the M2 space we have to put another atom which is bigger than magnesium. So in which very common atom is bigger as magnesium and can be also incorporated very easily in the crystal structure. So just think about a few bigger atoms. So that is here the atom calcium. So the calcium has also 2 electrons in the outermost ring like the magnesium, so you can balance it very easily. So and here we have the -12, yeah? So and now we are making a Hedenbergite, and what you are thinking does this Hedenbergite looks like? Which very common exchange vector we can use? We are using the Fm exchange. So and then this Hedenbergite, that is then here a calcium again, yeah? 2 plus. Here we are making the Fm exchange, 2 plus. Then we have here Si4 plus, O6, 12 minus. So and then the Hedenbergite is finished. So and you will, he will also do this then in the practical with you, yes, to train how to write down these mineral formulas that you get a little bit familiar with it, yeah? So and then we are putting the Jadeit together, yes, the Jadeit. So now we have already done the magnesium-iron exchange. So maybe we can exchange here on the M2 space, we can put in another atom which is even bigger than the calcium. So in which alkali metal is bigger than the calcium? No, aluminium is smaller, but it's good that you are saying aluminium because we will need the aluminium in a few seconds. Aluminium is nearly of the same size like silica. So that means you can put in then the aluminium on the M1 space and on the tetrahedron space. But which atom is then bigger? Also an atom which is very common in rock-forming minerals. Which one is bigger than the calcium? What? No, magnesium we have already used up. Bigger. So that is for example the element sodium. So then we have Na, but we have now a problem because the sodium has only 1 electron at the outermost ring. Yeah? We have only 1 electron in the outermost ring. We have here silica 4 plus. Here we have oxygen with the -12. So and now it's your turn. Because we have now to make an electron charge balance. So we need now an atom which has nearly the same size like the silica and has nearly the same size as the magnesium and has 3 atoms in the outermost ring. That is now the aluminium. Yeah, because we have to balance it, because the sodium has only 1 electron in the outermost ring and the calcium from before has 2. So then we have to put in something with 3 electrons in the outermost rim, and that we are doing just now. So then we have Al, and the Al atom has 3 plus. And then our Jadeit is finished. So you just write these formulas in the practical, and then maybe sometimes at home again and again in the same style as I'm telling you, then you will get them very easily and very fast. It is one of the most simplest things on this planet. So and now we are making from our Jadeit, we are making now an acrid. We have here also the silica with 4 plus. Here we have the O6 minus 12. So and here we are putting then also the sodium again with 1 plus. So and now we are exchanging the aluminium with another element which has also 3 electrons in the outermost ring. And which element could that be? Yes, we know. That is the iron 3 plus. So and then our acrid is finished. Fe 3 plus. That's the way how it is. So and of course you can then also replace this aluminium and the iron 3 plus. You can also replace with chromium. Yeah. Then you have another pyroxene which is then called the fuchsite. Yeah. And so you can exchange all these elements. You have just to use the periodic table, and in the periodic table there is written how many electrons in the outermost rim. Yes, because you have always to make the electron charge balance, because if this does not fit with the electrons, with the negative and the positive, then your mineral will fall apart. So that happens when we are talking about weathering of minerals. Yeah, you can see rocks in the field which are just falling in pieces. Yeah, and that means certain atoms becoming removed from a mineral. For example, the K-feldspar in the granite. Yeah, granite is very sensitive of weathering, yeah, or alteration, and that means water is penetrating the rock. Then the potassium, in this case of weathering of K-feldspar, the potassium becomes removed, and then our K-feldspar is full in pieces, yeah. So and then you get just a lot of small sand grains, and then you have made from your igneous rock a sedimentary rock. So and these all can be described by these simple chemical things here. So these are now the most common and for us the most important pyroxides. Are you done with this? Yes? So and now we will do a small jump. I will now not continue with the double chain silicates, because there I have about, I don't know, about 20 end members. Yeah? And for them I need 1 hour extra. So we will now continue with the sheet silicates. So the amphiboles, the mineral chemical structure of the amphiboles, we will then make next week in the 1 hour. So now we will just continue with the micas, because the micas I can finish by now. The micas, they are sheets of tetraedras, yeah? So and we have micas, we have here the micas, we have the talc, the clay minerals and the serpentine. Here the tetraedron cannot be seen because it is too dark on the picture, but you can see it here. Here you have always these rings. So and these are a lot of different sheets of tetraedrons. So and in nature it looks like follow. We have here somewhere a biotite. We have a biotite that is a 3-octahedral mica, and we have the muscovite, that is a p-octahedral mica. So, right is here. So where is the biotite? Here. There we have a muscovite as well. Then we need a biotite. This is maybe here. Here is a phototype, but we have a better piece. Here it is. So, here I have 2 big pieces. So just let it go out. So here I have 2 pieces. The dark piece is a biotite, and the silver shiny piece is a muscovite. So the biotite, that is a 3-octahedral mica, and that is a d-octahedral mica, and I will show you why this is. So, and here, if you are watching it from this side, you can see all the different sheets. So, and these are the sheets reflecting by the internal structure of the atoms, yeah? So, and if one would do it, one can remove sheet by sheet, yeah? So, in former times, a few thousand years ago, the people, a few thousand years ago, they used these sheets to make then the sunglasses. No, it's not a joke. They use these sunglasses, yeah? Girls usually use d-octahedral micas as sunglasses, whereas the boy used the 3-octahedral mica. So, and now we are looking at these sheet silicates, yeah? One have to say sheet silicates and not shit silicates. So, and there I have somewhere another very nice figure where one can see it very, very nicely. Let me just check it where I have it. Meta 1. Here we go. So here we have such a sheet silicate. So here we have a sheet of tetrahedrons, yeah? Here we have the next sheet of tetrahedrons, and here we have an interlayer, yeah? So then we have here the next sheet of tetrahedrons, here we have the next sheet of tetrahedrons, and here we have atoms between. So in these light bluish bubbles, that is the OH. So because sheet silicates, they contain water, yeah? Like the amphibolites. So and here that is the OH, and here we have this reddish bubble inside, and that is in this case a metal, and in this case it is the magnesium. So and now we have to write it down in such a way that we can understand. Here I put this square, yeah? So in this square, that is here the interlayer. So that means we have this interlayer, and this interlayer is empty because you can see there is no atom sitting inside, yeah? So, but in the biotite, there is an atom sitting inside. So, and now we have here the Si, the tetrahedrons, and the tetrahedrons we have in the sheet silicate, we have always 8 tetrahedrons. 8. So, and what is sitting on this tetrahedron? Silica. Yeah? So then we have here the silica. So, and here we have 8 silica. So, and then we have here this bluish, light bluish bubble here, yeah? And I told you that is OH. So, and every sheet silicate on this planet, in every amphibole on this planet, has an OH2 group. So, without knowing nothing about all these sheet silicates, you know every sheet silicate has 8 silica and has 1 OH2 group. You can just write it down blind, yeah? So, and then we have our octaeder spaces, and these are the octaeder spaces, and on this figure all the bubbles, the red bubbles, are all of the same size, yeah? They are all of the same size, and there is only this red bubble inside. That means we are talking here about the same atom, yeah? So, and these are then our M spaces. And the M spaces, I told you, we have bigger M spaces and we have smaller M spaces. The small M space is always the M1. So in the smaller M space, we can then put the same atoms or nearly of the same size like the silica. Yeah? That is the exchange with the aluminium. Yeah? And now I will introduce a new exchange vector. So, and then we have here the M2 spaces. So, and now we are making our first mineral, and we are making now a phyllosilicate, and that is the mineral talc. So, and that is how the talc look like. That is here we have an Mg, here we have an Mg, and here we have an Mg. So, and now the talc is finished. The talc is an Mg3 Si8 OH2 mineral. Yeah. That is the type. So, and now we are we are making now the three octaedral micas. So, in the three octaedral micas, this is the biotite. So, and this is the black one, which I just gave you around the black one. Yeah. This one, which the boys are using for the sunglasses 2000 years ago. So these are the three octaedral, and that is the this group is called the biotites, biotites. So and here we have 4 end members. I will just give you the most important 4 end members, and that is the phlogopite. Then we have the anite. Then we have the siderophyllite. And we have the histonite. So, and now I will show you the next figure how such a 3-octaedral mica look like. So that is now the 3-octaedral mica. So, and if you are checking the figure from before, then on this figure is something different. So, and what is different? Yes, there's something in the interlayer. So, and these are these big bubbles. These big bubbles, they are in the interlayer, and therefore they are called the 3-octaedral micas. Yeah? There is something here inside, and if we are talking about micas, then it is the element potassium. Here we have a potassium, here we have a potassium, here we have a potassium. And the potassium has, like the sodium, 1 electron in the outermost rim. Yeah? So that means we have now additionally 1 electron more. Yeah? So if we have 1 electron more, then we have to make somewhere a charge balance. Yeah? So and where do you think we can do the charge balance? So if we are talking here about the phlogopite is the magnesium-rich end member. We have here a magnesium, yeah? On the M2 spaces. So, but here on the M1 space, I told you the M1 space is smaller than the M2 space. So we can make in smaller atoms, yeah? Maybe the atom with 3 electrons in the outermost strip. And this atom we can also put in the tetrahedron space to remove 1 silica. And then our thing is finished. Here I didn't make brackets. Here again the OH2. So, and then we have here Si7. Then we are putting here 1 aluminium inside. And here we are putting also, instead of the magnesium, 1 aluminium. No, that is wrong. Sorry. Here we are leaving the magnesium, yes. But here we are just removing one silica, because silica is 4 atoms in the outermost strip. We are removing one silica and adding one aluminium. The aluminium has only 3 electrons in the outermost strip, and then the mass balance or the charge balance is done, yeah? So that is always the game. So and now we are making from our phlogopite the anide, yeah? So which famous exchange we are using? We are using the FM exchange. So that means that's always the same. We are writing here Fe, Fe, Fe. So Al, Si7, OH2. So and now our anide is finished. So and the interesting thing is the phlogopite is then formed at higher temperatures, whereas the anide is formed at lower temperatures. So and if we are doing that, or what if we will do it, you can see this then also in thin section, yeah? Because the phlogopite is brownish in thin section, whereas the anide is greenish in thin section. So only by watching through the microscope without doing any mineral chemical analysis, then you know if you have a brownish biotite, then you know this rock or this rock has equilibrated at higher temperatures, that are saying if it is really brownish, between 700 and 800 degrees Celsius, where if it is really greenish, then this biotite was formed maybe between 400 and 500 degrees Celsius. So now we are making the siderophyllite, yeah? So and now I have to introduce the next exchange vector, and that is a very, very important exchange vector, that is the Czermak substitution. Czermak. Mr. Czermak was an Austrian petrologist, maybe 150 years ago. He is now also down. And he introduced this exchange vector, and that is a magnesium plus silica will be replaced by 2 aluminium. So, and if we are replacing magnesium and silica by 2 aluminium, that means aluminium is a smaller atom. The volume of one atomic unit will become smaller, and if we have then the Czermak substitution, that means your biotite was then formed at higher pressures. Yeah? So, and then we are putting here one smaller magnesium and here one smaller magnesium, but now we are making our Czermak substitution. We are replacing here one magnesium by an aluminium, then we are making here, and we are putting here additionally an aluminium inside, and we have here 2 aluminiums, and we are removing one silica, then we have here Si6. OH2. Yep. So, and now we are making additionally to our Czermak in the substitution, we are making now the FM exchange. And if we are making here the FM exchange, then we are replacing here the magnesium by iron. Yeah? Iron Al2, Si6, OH2. So, and these are now the 3 octahedral micas. So now we are doing the d-octahedral micas. So these are the silver shiny ones, yeah? These are the silver shiny ones. So, and we have 4 d-octahedral micas. So, and I just told you before that the magnesium, that is biotite, if the biotite is very brownish under the microscope, then it is a magnesium-rich one, whereas when it becomes greenish, then it is the iron-rich one. So, but now I gave you just also a sample of a d-octahedral mica. And this is silver, so or silver to glassy, yeah, and silver to glassy means we do not have longer magnesium and iron in the system. So then we have to think about what we can do next. We can replace our zinc with aluminium. So and then we are making at first the phyllite. So that is the phyllite, and the phyllite has then here also an empty space, yeah. So the phyllite, that is just an exchange with the magnesium here. So and if we like to exchange 3 magnesium, then we can here we have 2 plus, 2 plus, 2 plus, and now we have a d-octaedral mica. And if we have a d-octaedral mica, it is called d-octaedral because the M1 space is empty, yeah? So here we have a 3-octaedral mica because all 3 octaedral places are full with atoms, yeah? And if we are talking about the d-octaedral mica, then we have only 2 octaedrons which are filled up, yeah? So and the ones which is not filled up, that is the M1 space. So but we must put here electrons with 6 atoms, atoms with 6 electrons in the outermost ring. Then we are replacing here with aluminium. Yeah? So then we have 3 plus 3, and here we have 2 plus 2 plus 2 is 6. So then we have here the Si8OH2. So and then our phyllite is finished. Then we have as next the muscovite. Then we have the muscovite, and then we have the paragonite, and we have the margarite. So if we are putting now a muscovite together, then we are putting here an atom on the interlayer, yes, again here, and this atom which we are putting here in the interlayer, that is potassium. Then we have here Al3 plus, Al3 plus. Here we have our space because d-octaedral mica. We have here, then we must make here a balance. We are putting here an aluminium on the tetrahedron side, Si7OH2. And our muscovite is finished, yeah? So now we are making a paragonite. So in the paragonite, where we have still the aluminium on the C spaces, on the aluminium on the N2 spaces, and what we can do next, we can put another element here in the interlayer, yeah? So and which other element is nearly of the same size like the potassium and has 1 electron in the outermost rim? Sodium, yes. You got it by now, yeah, that is all very easy. Then we are putting here a sodium, we have here the 2 aluminium, here we have our empty space, aluminium, Si7OH2. So and now we are making a margarite. So and which element is also nearly of the same size like the potassium, but unfortunately it has 2 electrons in the outermost rim. Calcium, yes. So then we have here the calcium. So but now we have here the calcium, and you know by now the calcium has 2 electrons in the outermost rim. Here the space is empty. So what we can do here, we are now making the calcium charmak. Calcium charmak. So that means we are replacing calcium plus silica with 2 aluminium. So, and that means we are putting here we are removing 1 silica more out of the system, and we have then here 2 aluminiums on the tetrahedron side, and then our mineral is balanced. So, and these are now, we are now finished for today. That is the sheet silicate. Then we have just to do next week on Thursday, we have to finish it with the amphimolds, and then we have this. and then we can write down some typical reactions. Then you can see how these different minerals or mineral reactions taking place. Yeah? For example, if you are dehydrating a muscovite, if you are dehydrating a hydrous mineral, then you are removing here the OH, and if your muscovite is dehydrating, then you are forming a K-feldspar. If your paragonite is dehydrating, then you are forming an albite, and if your margarite is dehydrating, then you are forming an anorthite. Yeah? So is the whole thing is linked with each other. Okay, done.